Now look, I don't care how rigid your tool is. If you haven't got control of exactly where you're poking it, what chance do you have of making a precision part? 2 years ago, I built my very own computer numerically controlled milling machine from scratch. But the fact that I'd never actually used one before meant that I really had no idea what I wanted to be able to tell it to do. And while I've certainly been able to produce some usable parts with the original controller, the experience has always felt like it's been missing something. Until now. Before we jump into the meat and potatoes of what it takes to assemble a universal, industrial-grade motion control system, complete with closed-loop encoder feedback, touchscreen interface, and yes, an RGB keyboard, or indeed why you'd even want to do such a thing, you should know that I'm not an engineer. Electrical, mechanical, or otherwise, so rest assured. This video isn't so much a how-to, as a how I suffered through close to 500 hours of stubborn refusal to give up on getting this machine to do exactly what I want it to, with little more than a soldering iron, a questionable grasp of electrical standards, and a willingness to succeed. Okay, I'll admit, there was definitely a little more to it than that. Oh, following error. It's meat and potatoes time. At the most basic level, a computer numerically controlled system is just a way to tell motors where to go and when to get there. You've got a computer, obviously. You've got motors, as I mentioned. And in between, a controller that turns move here into exceedingly well-timed pulses of electricity. The simplest setup might move a machine from A to B and call it a day. And in a lot of cases, that's enough. Of course, if your goal is anything beyond a glorified Etch-a-Sketch, there's a little more to it than that. But all you really need to know right now is that when I first built this machine, much like the punchline to some kind of epistemology joke, I just didn't know what I didn't know. But I'm far from prone to prolonged satisfaction, so it didn't take long for me to realize that the limited parameters and pins present on my first attempt at precision machine control stood stubbornly in the path of such thrills as closing the control loop with real-time encoder feedback, or storing tool length offsets in a table to avoid the 30-second probing routine every single tool change. And don't even get me started on this thing. The good news is, this Mesa 7995T promises to solve all of these grievances and more, but testing those promises was going to be a little more involved than just swapping out controllers. The original electronics were housed in a steel cabinet, bolted to the side of the machine stand. It was a decent attempt, but one made with little consideration for the impact of future maintenance on the integrity of my lower back, and well before I ever ran coolant on the machine. But even putting the issues of accessibility and aquatic incursion aside, there simply wasn't enough space for a straightforward retrofit, let alone any future additions. So at some point, the decision was made to build a standalone rolling cabinet that could house the entire control stack, tidily solving all of these problems at once. At least that was the plan. 2 off-the-shelf enclosures formed the backbone of this would-be command center, and a couple of custom welded frames made sure there'd be ample opportunity to route cabling, attach casters, and ensure that controls were just slightly too low, allowing the operator to assume the proper stance. Now, I'm a big proponent of the idea that you should always do your best with the tools you've got. So I was pretty much morally obligated to take advantage of my employer's latest acquisition, a nice big box and pan brake, to bend up the hinged front panel for our control stack. This thing got a lot of use throughout this project and saved me an immeasurable amount of time and frustration, which almost cancels out the immeasurable amount of scope creep and frustration it created. But we'll have to circle back to the stainless steel saga a little later on. Now, as sexually gratifying as this sheet metal component had become, it wasn't going to be very useful without anywhere to mount the buttons and knobs that every control panel adjacent doohickey is legally required to include. And hopefully it's obvious that there's a fundamental incompatibility between electronics and swarf, so I couldn't really go any further, let alone reach completion, without ensuring adequate penetration. Mounting a touchscreen monitor was simple enough, with the 2 holes only requiring a slight amount of relocation. But while I knew I'd definitely need space for several knobs, I still hadn't formed a complete picture of exactly what functions would make the final cut. And I really didn't want to commit to a button layout before I'd had the chance to actually mess around with the new control software. So after a little arbitrage with the jigsaw, I had myself the perfect perforations for a pair of removable panels, squarely placing the responsibility of deciding where the buttons go on a version of myself not yet burdened by such frivolities as present existence. Of course, we'll certainly meet that man, but before that, we've got a whole lot more to put on his plate. At this point, it's probably becoming clear that my so-called plan for this upgrade was closer to a vision board than a blueprint. A fact perhaps best demonstrated by the amount of time I'd spend staring at mock layouts over the course of the ordeal. The most immediately obvious constraint is simply space. You've got to be able to fit all your components, trunking, and copper. Ideally with space left over for a little scope creep. On its own, that's no big deal. When sizing a cabinet, you can just use this equation as a rule of thumb. Take n plus e to the I pi plus 1.1, where n is the size of the cabinet you've already bought. But things get tricky if you're going to consider things like heat output and electromagnetic interference between your high and low voltage conductors, which you should definitely be considering. I mean, yeah, chucking a fan in can cool things down, and properly grounded shielding should minimize unwanted voltage spikes in your signal cables. But the best solution is physical space, which is completely at odds with our primary goal of, fitting everything into the box. If you like fitting things into boxes, you should like the video. And if you subscribe, I'll know you want to see more. Now, to be fair, this time around I definitely had a broader understanding of all the kinds of wiring aids and infrastructure that might help, like these multi-level push-in terminals, slimline relays, and DB connector breakout boards, which I didn't even end up using, by the way. And the decision to include a second enclosure dedicated to the low voltage signal and data connections of the motion controller, and I had quite a lot less to worry about as far as noise was concerned. But I could never quite shake the feeling that there was some obscure connector or mounting trick just out of reach. And in the end, even an entire second box failed to skirt the universal truth that there's never enough room. The fact that you're seeing this video means that I did eventually manage to land on a layout that wasn't completely objectionable, if only for a brief moment. But that brief moment was all I needed to once again move forward on the project. With the panel layouts temporarily finalized, I could attach my DIN rails and custom cable trunking. It might seem like an odd choice to 3D print this part of the project, but I had an absolute hell of a time trying to source the good stuff locally. And besides, this particular shade of orange does a fantastic job of conveying the possibility of instant death, should you go poking around with the power on. See, the main purpose of this lower cabinet is the switching and distribution of 240 volts AC, which means relays, contactors and power supplies. All the high voltage, high consequence stuff. First of all, we've got a main isolator, which just disconnects power from the cabinet entirely. That's our first line of defense when things start to smell funny. Next in line, we'll find a 16 amp miniature circuit breaker. In the case of an overload or short circuit, it won't necessarily save all the downstream components, but it might just spare the cabinet from complete self-immolation. From there, power flows into the first of 2 AC buses. This will handle the always-on loads, like the DC power supplies, the cabinet fan, and a few other background players. Then there's the safety relay, which acts as a kind of bouncer for the next stage. It's constantly watching for an e-stop or fault condition, and if triggered, it'll drop out instantly. That safety relay controls a big old 63 amp contactor, which feeds the second AC bus. This bus powers everything that should absolutely not be on in an emergency. Drives, motors, and anything else with the potential to cause motion or mayhem. It's a straightforward structure that ensures critical systems systems get cut off fast, while the support hardware stays alive to report what went wrong. It also means I can work on the software configuration without any risk of amputation, conflagration, or castration, although prostration's never off the table. On the topic of critical systems, proper earthing is essential. Was that enough gravitas? Proper earthing is essential because if you don't earth the machine, you will earth the machine. But the terminology surrounding correct earthing practices read like a forum post that assumes you were born holding a fluke in one hand and anything but a broom in the other. So in a desperate attempt to minimize liability, all I'll say is that on my machine, all earth connections run to a single dedicated earth bus, which is then tied directly to the cabinet plug earth. Once the bones of the cabinet were in place, it was time to start wiring. And this time around, I was determined to stay ahead of the chaos. So aside from ferrules to tame the stranded conductors, every single danger noodle got heat shrink labels on both ends. At least until I ran out of heat shrink label. I won't get into all the ins and outs of the motion controller panel yet, because by the end of this video, it's going to look completely different. But the basic idea of all of this is to provide access to all of these, hopefully making troubleshooting and reconfiguration a fastener-free affair. It's always a good idea to do as much work as possible with the removable panels, well, removed from their enclosures. But with the technology to phase cables through cabinet walls still a few years out, there's always a limit to how long you can avoid triggering your chronic back pain. So once it was time to start running connections betwixt my panel pair, it was into the belly of the beast for the both of them, marking the start of a very different kind of wiring session. No longer standing tall at the bench with everything laid out neatly, I was now crouched down, hunched over, and shoulder deep in an awkward tangle of trans-cabinet cabling. My only saving grace was the short-lived nature of the bout, thanks to the continued absence of extensive planning and the as-yet undecided pin-out between the cabinet and the machine itself. But if the progress so far could be likened to a frying pan, the next step was shaping up to be the fire. And this juicy piece of meat had no idea what he was in for. The stack of industrial connectors I'd collected, ranging from 3 pins to a whopping 26, offered a staggering amount of flexibility in the matter. But before I could get to the satisfaction of just plugging it in, there were a whole lot of decisions to be made. How many wires per subsystem? How many subsystems can I fit in one cable? Do I really need an isolated ground reference for every signal? The chain of dependencies was longer than a piece of string, and twice as chainy, because now I also had to think about the other half of the equation: junctions, cable routes, and mounting surfaces on the machine side, none of which were particularly well accommodated by its OEM podium. A product of afterthought and available steel, the base of my precision machine was only ever meant to serve as a temporary solution. But nothing is more permanent than a temporary solution covered in connectors and cable, so there was no choice but to build a new pedestal, just slightly more fit for purpose. And if I was starting from scratch, I figured I should probably have a proper think about how it might accommodate an enclosure down the line. Actually, forget down the line. There'd never be a better time to tame the torrent of tiny needles and flood coolant than right now, with free reign of a pan brake and a stockpile of surplus mild steel sheet. Actually, forget the mild steel sheet. I was in for a penny, and stainless steel was only £1. Figuratively, of course, this shit is crazy expensive, but the scope creep had taken me by the neck, and before I knew it, I'd committed myself to encapsulating the magic of the new controls concurrently to cabling them in beautiful, shiny, marine-grade 316. Now, it's easy to lose momentum in the face of massive projects like this. Luckily, I've got these motivational metal posters to keep me going from today's video sponsor, Displate. Displate produces premium prints on real metallic metal because your passions deserve more than some flimsy non-metal or non-committal metalloid substrate. They've got a truly ridiculous number of designs, including officially licensed art from all your favorite fictional universes like Star Wars, Marvel, and the moon landing, as well as original designs from thousands of artists all over the world. So there's something to suit every space, special interest, and individualist. And with lightning fast delivery, there's no need to plan ahead. You can should have a stack of disc plates on your door within 5 business days of ordering. When it's time to hang your designs, you won't need an engineering degree. Mounting them to the wall takes seconds with the included magnet kit, because if you'll remember, they're made of metal, and metal is attracted to magnets. And make sure you check out their texture line that has 3D texture built right in. Don't believe me? Take a look at this. That's a whole 200 microns of added contrast and vibrance. These designs would leap off the wall if it wasn't for the, metal and magnets. There's nothing quite like a pat on the back from a metal poster with more than enough style to pass for personality. So use this code for 37% off 3 or more disc plates using the link below. We'll take a closer look at the features of this monumental side project as they become relevant. But with the fabrication of the frame complete and a newfound appreciation for life outside of the sheet metal trade, it was time for some rigging. Now, as you may know, I recently added a fair bit of weight to the machine while upgrading the spindle, putting its total weight just outside of my comfortable lifting range. Thankfully, I know a very large man who was willing to help me out, and he's got an engine hoist.
300. 450. 480. Yeah, 480.
You win. It didn't take long, no more than half a day or two, to get the machine lifted, shuffled, and bolted onto its shiny new pedestal. And for the first time, it looked like it actually belonged there. Once the thing was did, I could finally start thinking about where to mount everything machine side. But before we go any further, I should mention that up until now, separating this story into a step-by-step account of challenges, revelations, and resolutions, arranged in a roughly chronological order, has been relatively straightforward. That's about to change. See, with the machine in place on its new stand, all of a sudden I had a dozen half-complete components clamoring for attention. The only thing keeping me sane was the freedom to bounce between tasks, mechanical, electrical, and existential, depending on which one had frustrated me least that day. So for a little while at least, we'll be traveling not just through the project, but across it, on a timeline fractured by indecision, traversing the creative coping strategies of a man or several men for whom task priority and continuity were a distant memory. Arguably the largest contributor to the chaos of my so-called to-do list was the completion and subsequent installation of the stainless steel panels that will form an enclosure. Their addition would hopefully keep the coolant off the floor and the chips out of my flesh. But while these are two undeniably huge improvements in the overall state of the workshop, the goal of getting the machine moving again, which required wiring around the panels, was still the most important by far. So installation came first and completion a little later. I'd given a lot of thought to the design of these parts, but not by choice. Their form was a delicate balance between size, aesthetics, and the unyielding proclivity of shit to flow downhill. But it still lacked a lot of details as far as how it would actually, attach to the machine. We could certainly spend hours talking about the hundreds of minute decisions and changes, like these stiffening brackets or those ones. But all you really need to know is that my failure to plan quickly became a plan to plan, and planning while doing meant dozens of hours of offer-ups, test fits, and adjustments before I even attempted to weld up the corners. See, my usual sense of general overconfidence had been rudely interrupted when my practice attempts to fuse this new-to-me exotic material failed to produce anything that could reasonably be described as a weld, instead more closely resembling the south end of a north-facing dog. Eventually I found some success with the help of some heat sinking combined with the pulse setting of my welder. I certainly did my best, and Sikaflexed the rest, but it'd still be a while until I'd know if they held water. Somewhere around the earliest test fits of the drip trays, I started to form a picture of how all the machine side wiring might get to where it was going, not to mention where it would all come from. I'd intended to make use of some smaller steel enclosures to mount the myriad of incoming connections and house their corresponding terminations, but no amount of offering up could seem to produce a picture of the elegant electrical installation I was shooting for. If I put it here, it's going to get covered in coolant. And if I put it here, I can only get to it if I move the machine. I eventually realized that my problem lay squarely in the boxes themselves, and the only way to maintain accessibility to the wiring within, without compromise on ideal overall placement, would be a lightweight, low-profile, hinge-free alternative, or two, mounted to a pole, chest height, at the rear of the machine. Obvious, if you think about it for a second. With the origin of its electronics defined by the panel connectors at the front and cable glands at the back, the foundations for the machine-side control circuitry could finally begin branching out. The first split in the signal loom occurs right behind each junction box, with motor control cables for the stationary Z-axis motor heading right up to the tippity top of the column within the cozy confines of some flexible conduit. The run for spindle motor and milling head related paraphernalia takes a slightly different path, its conduit converging on the drag chain with the help of a clever cover simply clipped in place. Coolant and compressed air will join the party here soon as well, but the rest of the cables are carried in a common duct, completely concealed from chips and coolant, down and then across to the Y-axis chain mount, where power for the front to back axis motor and coolant pump will go their own way. Things are really moving now as we chart a course towards the XY intermediary plate. Via the combined double-ended drag chain mount and ducting, I'll call the reach around. With no time like the present, the homing sensor mounts and flags received a long overdue refresh, and their signals routed out the end of the reach around alongside a pair of protective earths. A pair of glass scale encoder cables joined them a little later, when no time like the present had almost passed, and the regret of choosing to get around to it later paid visit to a dream. The enclosed X-axis chain was the last leg, and presented a number of unforeseen and unprecedented clearance issues. Because while clearance is clearance, interference is not.
That's not gonna work.
Though a little bit of cutting, grinding, and extra stainless steel was usually enough to put things back in the black. And finally, connections for the X-axis motor, tool height probe, and table earth are routed out the end of the now unimpeded drag chain, along with a just-in-case 16-core cable to hedge against the possibility of further scope creep and table-related sensing requirements. Now, to tell you the truth, we've gone over that a little backwards. See, the laying of each cable had started at its endpoint and wound back from there to the pair of boxes I mentioned earlier. But that makes no difference to the fact that I now had to fit every single one of the machine's connections, preferably impermanently, inside a space no bigger than this book of 40,000 quotations. I'll be the first to admit that a custom printed circuit board or two would have been the go here, and in plenty of other places all over the machine, and I'd love to properly figure out how to design them one day. I've just been too busy building this time-saving machine to stop and learn how to save time. For now, I just have to make do with a little perf board, a screw terminal or two, and a whole lot of soldering. At this point, the machine's pinout was about to become permanent. But keeping track of over 100 signal and power connections was going to be impossible without some kind of coping strategy or system. Mine came in the form of a bunch of scrawled lists that I could have sworn is around here somewhere. With each pin of each connector finally defined and its function documented, more or less, the soldering that followed was almost like meditation. I mean, I know they look intimidating, but there's nothing too tricky about wiring up these connectors. A bit of flux goes a long way, and forward thinking is helpful, because it's definitely possible to solder yourself into a corner. But that's avoidable by just working left to right, or right to left, depending on the hand you use to pick your nose. And before you do any soldering, it's a good idea to triple check the cable for the presence of the connector's back shell and the retaining nut.
Absolute classic.
But as simple as the task might have been, by the 36th connector and the 412th soldered pin, any chance of spiritual enlightenment had well and truly burnt off. Matters of transcendence aside, I now had every necessary input and output required to run the machine connected and secured. I was feeling fairly confident in my work, but that didn't make the next step of powering everything up at once any less nerve-wracking. One shoddy solder joint, misterminated cable, or metal shaving was all it'd take to nullify hundreds of hours of work. There was a part of me almost unwilling to take the risk, but my magnum opus was a machine tool, not a museum piece, so I plugged it in, flip the switch, and hit the start button. The system was energized, and so was I. Once it was clear the smoke had remained securely within each and every component. Of course, nobody's perfect, and somewhere in the monotony of the job, I'd managed to mix up the X and Y axis motor connections. But I wouldn't find that out until later. Now that everything had power, it was time to take control. But there was still a fair bit of brow furrowing standing between me and that bright white cycle start button. I mean, for starters, there still wasn't anywhere for it to go in the control panel. Now, I spent a lot of time contemplating the layout before I put whole sorter panel, but only after this decisive action did I realize I'd unwittingly been thinking about the worst way to do it. With my sheet metal reserves running as thin as my patience, and no promise that a second attempt would be any less disappointing, I turned to my 3D printers for salvation yet again. The removable panel became a removable panel, populated by one small and one large print, which, through the power of computer-aided design, would be almost effortless to adjust. Then all I had to do was wire them into the controller, and bada bing bada boom. They do absolutely nothing. See, while Linux CNC, in combination with a Mesa FPGA board like this here 7995T, is one of the most powerful, flexible and precise motion control solutions available, it won't do a single thing without explicit instruction. But I mean, every CNC machine is going to require some level of configuration at the software level, and that's true whether you're running the lightweight but mighty Gerbil HAL, or something like the colossally costly Masso. In order to simplify this configuration, products like the Masso place a whole boatload of restrictions on how their controller operates. So the process amounts to not much more than modifying a list of parameters. Stuff like how many pulses does an axis need to move a millimeter, which direction should it search for homing switches, and how fast it's allowed to move to suit your machine. This simplicity sounds great, but the fact is, if you want control of your machine's operation beyond the scope of their list of parameters, you're shit out of luck. In theory, Gerbil HAL offers a compelling argument for the open source side, with an incredibly low cost of entry and the option for custom implementation available to everyone through its hardware abstraction layer. But in reality, its relative infancy means that for anyone but the most dedicated developer, you get what you get and you don't get upset. Linux CNC, by contrast, isn't afraid to put the burden of clarity on you. It won't assume, interpret, or interpolate. Every input and output, every logic gate, every single connection between your machine and the world is defined by you, in plain text. I know that sounds intimidating, but it's really not that hard. Okay, I can't say that my experience of the learning curve was anything other than integration hell. I mean, even ignoring the CNC side of things, Linux has its own fair share of challenges. It took the better part of a day to figure out how to rotate the touch input on the display, and I'm still clueless on how to have the requisite script run automatically at startup. But the level of configuration it allows is basically unmatched, at least for the price. Want to check for spindle motion before engaging the drawbar cylinder? No worries. Want to monitor machine temperature to actively compensate for thermal expansion? This guy's done it. Need to lighten the mood when you break your next end mill? Well, you could. Even the interface is up to you, though on this point I ultimately decided to take advantage of someone else's hard work to get my greasy paws on this slick-looking touch interface. The wealth of documentation and community development meant it wasn't long before I had the PC talking to the motion controller, and a basic intuition for the language and structure of the hardware abstraction layer followed closely, behind a modest amount of trial and a truckload of error. Starting with the basics, like homing switches, axis scaling, and actually wiring the motors correctly, I slowly but unsurely worked my way through each subsystem, connecting the motion controller's physical I/O to HAL-based signals and pins. Then it was on to the interlocks and add-ons, using a time delay function to prevent rotating tool ejection, linking the flood coolant UI pin to a relay that, in turn, switches a woefully underpowered flood coolant pump.
My pump's not strong enough.
Then later, its more capable successor. And perhaps most noteworthy, replacing the X and Y pseudo-position feedback input with the actual physical axis encoder position. See, ordinarily in an open loop control system, your motion controller is just pulsing into the void, hoping that whichever step and direction drive may be receiving your transmission is 1, capable of following the instruction, and 2, willing to do so. By adding linear encoders to the control loop, we let the controller follow up on those instructions, sort of like a performance review. If the motor is struggling to keep up, the controller sends more pulses as encouragement, and any initiative in the form of overtravel is quickly quashed by a reduction in pulse instruction. And if the axis is too far outside of where it should be, we get a following error. And I got a lot of following errors, but PID tuning aside, as it always should be, and despite the continued absence of planned features like the spindle encoder, pressure sensors, and the control panel jog functionality, the controls were now beyond fully operational, at least compared to their previous iteration, and I was dying to see if it was all worth it. Spoiler alert. It was totally worth it, and while the list of things I wish I'd done differently is twice as long as the list of things I learned along the way, those improvements will just have to wait. Inside a space, no booger. I need a camera on your face laughing at me. Much like the punchline to some kind of epistemology joke. I just didn't know what I didn't know.